Welcome, my friends! I'm so excited because in this video we get to introduce hypothesis testing, which is one of the largest areas of statistics. So let's go ahead and get started. Let's begin with a motivating example. Let's say you're walking down the side of the street and you find a coin, and you decide to start flipping it. On the first flip of the coin, it lands heads face up. On the second flip, you get heads again. And on the third flip, you get heads a third time. Well, I don't know about you, but in general, I would assume that any random coin that I pick up is probably a fair coin, meaning it would have an equal chance to be either heads or tails. In hypothesis testing, the default position that you might have with respect to any situation is what is called the null hypothesis, in this case, that the coin is fair. But perhaps at some point you might start to challenge that null hypothesis if you encountered some situation or some evidence that contradicted that hypothesis. Let's say you continue to flip this coin and you continue to get heads a fourth time, fifth time, sixth time, seventh time, and an eighth time. So let's say you flip this coin 8 times and you got heads 8 times in a row. Well, if this was a fair coin, you'd expect to have half heads and half tails. So the evidence or data that we have collected is seeming to contradict this null hypothesis. Perhaps some other hypothesis, maybe an alternative hypothesis, that the coin is not fair is actually true. The question, of course, becomes, what evidence would convince you that the alternative hypothesis is true and that this is not a fair coin? Is 8 heads in a row enough to convince you that the coin is not fair? Well, for some people it might be, but for some people it might take more than 8 flips or maybe less than 8 flips. This is the setup that we will have for all hypothesis testing problems. We will always have a null hypothesis that will represent the default position. In science, this might be the historically accepted position that might have been established by other researchers. Then we have the alternative hypothesis, which somehow contradicts the null hypothesis. This is oftentimes called the research hypothesis. It might be the hypothesis that you put forward that you are trying to prove based on some data. Based on the result of some data, which might come from either a sample or maybe an experiment, you will decide if either the null hypothesis or alternative hypothesis seems more likely. Let's summarize some of this information. There are 2 types of statistical hypotheses. First, we have what is called the null hypothesis. Oftentimes, you will denote the null hypothesis with a capital H with a subscript 0. And this is typically going to refer to the default position that the researcher might want to challenge. On the other hand, we have the alternative hypothesis, which is denoted by a capital H with a subscript A, or sometimes a capital H with a subscript 1, which represents a claim that somehow contradicts the null hypothesis that the researcher would like to prove. Sometimes the alternative hypothesis is called the research hypothesis. Based on the results of an experiment or sample, we're going to make one of 2 possible decisions. First, we may fail to reject the null hypothesis. You should make this decision when the data is consistent with the null hypothesis. So if the results of your experiment are fairly consistent with what you would expect under the null hypothesis, then you will choose to fail to reject the null hypothesis. The other possible decision is to reject the null hypothesis. You should make this decision when the data is very inconsistent with the null hypothesis. So if the data that you've collected, either from an experiment or sample, is quite inconsistent with what you would expect under the null hypothesis, then you will reject that null hypothesis. Our decision should always refer to the null hypothesis, because that was the default position that we are challenging. We should always say that we are going to either fail to reject the null hypothesis, or we are going to reject the null hypothesis. And we should never reference the alternative hypothesis when we make our decision. Later on, we will be writing a conclusion statement that will reference the alternative hypothesis. The courtroom example is a common analogy used to understand the logic of hypothesis testing. For criminal proceedings, individuals who've been accused of a crime are considered to be innocent until proven guilty. That means that the null hypothesis, or default position, is that the individual is innocent of the crime they've been accused of. The default position for someone who's been accused of a crime is not that they are guilty. They are presumed to be innocent until they have been proven guilty. On the other hand, we have our alternative hypothesis, which would be that the individual is guilty of the crime. We have 2 possible hypothesis test decisions once we've collected the data. we will either fail to reject our null hypothesis if there is not evidence beyond a reasonable doubt. So if we don't have evidence beyond a reasonable doubt, then we're not able to say that this person is guilty. And we would say that we have not rejected the claim of innocence, or failed to reject that claim. On the other hand, if there is evidence beyond a reasonable doubt, such as DNA evidence at the crime scene, then we're going to reject the null hypothesis of innocence, and we're going to conclude the alternative, that this person is most likely guilty of the crime. Most of the hypothesis tests that we will conduct will not be written out in words, but instead will be written out using statistical symbols, such as mu or p. For example, let's say that a beverage company claims that their product contains 67 ounces of liquid. There are 3 different hypothesis test setups depending on what you believe to be true about the value of the parameter. The default position, which is going to correspond to our null hypothesis, relates to the claim that this beverage company has made, that on average, their product contains 67 ounces of liquid. There are 3 ways you could challenge this claim. You could either believe that the true amount of liquid that you get with this product is less than 67 ounces, which would correspond to a left tail test, greater than 67 ounces, which would correspond to a right tail test, or somehow different from 67, either greater than or less than, which would correspond to a two-tailed test. If we had a left tail test, we would have this set of hypotheses. No matter what, our null hypothesis is the claim that has been made, that the mean amount of liquid is equal to 67. The alternative hypothesis with a left tail test is going to be that the population mean is less than 67. Remember that the alternative hypothesis is the research hypothesis. This is the hypothesis that you, as the researcher, are trying to prove. So you would use this setup if you believe that the true amount of liquid that you get on average from this product is less than 67 ounces. Basically, you think this company is shortchanging you. The reason why we call it a left tail test is because eventually we're going to end up finding something called the p-value in the left tail of a distribution. We'll discuss this in more detail later. In general, you should use this setup, called the left tail test, when you believe that the population mean is less than the value that was stated in your null hypothesis. Next, we have the right tail test. The right tail test has the same null hypothesis, but now the alternative hypothesis has a greater than sign. You should use this setup if you, as the researcher, believe that the mean amount of liquid from this container is greater than 67 ounces. We call it a right tail test because you will eventually find a probability in the right tail of the distribution. You should use this setup when you believe that the mean is greater than the value stated in your null hypothesis. Finally, we have the two-tailed test, which is kind of like saying, I believe that the mean is different than what has been stated, but I'm not sure if it's larger or smaller. And for this case, we use a not equal to sign in our alternative hypothesis. Once again, note that the null hypothesis is not changing for any of these 3 tests. In all 3 cases, we have an equal to sign in our null hypothesis. If you chose this setup, then you would be finding a probability in both tails of the distribution. Typically, what you end up doing is finding the probability in one tail and then multiplying it by 2. You should use this setup when you believe that the population mean is somehow different from, either greater than or less than, the value stated in your null hypothesis. Now, we mentioned before that when you eventually conclude your hypothesis test, you could either fail to reject your null hypothesis, and you would do this when you believe that the null hypothesis was most likely true, or you could end up rejecting the null hypothesis when you thought that the alternative hypothesis was true. But just because we make one of these 2 decisions doesn't necessarily mean that was the correct decision. It could be the case that either the null hypothesis is true or the alternative hypothesis is true, and the true hypothesis does not necessarily have to correspond with our decision. Within this table that we've created, there are 4 different boxes. 2 of those boxes correspond to correct decisions and 2 correspond to errors. Pause the video and see if you can determine which quadrants are the correct decisions and which are the errors. Alright, hopefully you've given that a shot. Well, the very first correct decision would be if the null hypothesis is true and we were to fail to reject that null hypothesis, right? If the null hypothesis is true, then we should be not rejecting it. So this would be our very first correct decision. Going back to our analogy of the courtroom and the criminal trial, this would be like saying, oh, the person actually is innocent and we let them go. We did not convict this person. We could also have another correct decision, which would be over here. The alternative is true, and we reject the null in favor of the alternative. So this would be like saying, oh, the person actually is guilty of the crime, and we have convicted them, and that would be the correct decision as well. But then we have two other quadrants here, which are each going to be errors, and we label them with numbers. So first we have what is called the type 1 error. This would be if the null is true and we were to reject the null, sometimes called a false positive. So this would be the case where the person actually is innocent of a crime, but we put them in jail. That would be one type of error. We call that a type 1 error, or a false positive. Additionally, we have a different type of error, which is the type 2 error, which would be the case if the alternative was true, but we fail to reject the null hypothesis, right? If the alternative is true, we probably should be rejecting the null for the alternative. But if we don't do that, then we have the type 2 error. This would be the case where we have someone who actually is guilty of a crime, but we let them go free. And sometimes this is called a false negative. So type 1 error is like a false positive, and type 2 error would be like a false negative. Now we also assign probabilities to these errors. So if the null hypothesis is true, then the chance of making this type 1 error, the false positive, is represented by the Greek letter alpha, pronounced alpha. And we oftentimes call this the level of significance. Typically, this is a value that is set in a problem. We will set this value to either 0.05 or 0.01, which represents either a 5% or 1% chance of making this type 1 error when the null hypothesis is true. If the alternative is true, then you have the chance of making a type 2 error. And the symbol that we use to represent that is going to be the second letter of the Greek alphabet, which is beta. Now, if a problem does not state the level of significance alpha, you should assume that it is 0.05. Now, due to technical constraints, we can actually only set the type 1 error rate alpha, but in reality, we typically do not know what the type 2 error rate is of beta. So you might be wondering, if we can set the type 1 error rate, why would you ever set it to 5% or 1%? Wouldn't you just set it as low as you possibly could? Well, it turns out that the lower that you set your type 1 error rate, the higher the type 2 error rate is going to be. So if I set a 0.01 or 1% type 1 error rate, then my type 2 error rate is going to be larger, right, than if I was to only use like a 0.05 level. But all you really need to know at this point is that we have two different possible types of errors. The type 1 error, which is rejecting the null when it is true or a false positive, and we have the type 2 error, which is failing to reject the null when the alternative is true. And the symbols that we use to represent these. We have alpha, which is the level of significance, which is typically set to 0.05 or 0.01. And then we have beta, which is typically unknown, but we do know it's going to change based on how low we set the level of significance. If you're familiar with confidence intervals, you can kind of think of the level of significance as something similar to the confidence level. So whereas we might have had a 95% confidence level before, now we kind of have a 5% chance of making an error, which is somewhat similar to a 95% confidence level in our answer. So here is just kind of a comical example here. Maybe our null hypothesis is that the individual is not pregnant and that the alternative is that the individual is pregnant. A type 1 error, or a false positive, would be saying to someone who clearly is not pregnant, so the null is true, that they're not pregnant, telling them that they are pregnant. So this would be a type 1 error or a false positive, rejecting a true null hypothesis. That's how I want you to think about a type 1 error. Or the type 2 error would be kind of the opposite here. Someone who is clearly very pregnant, but the nurse here is saying, nope, you are not pregnant. And so this would be a type 2 error or false negative, failing to reject a false null hypothesis. All right, so here is a problem for you to try. Medical tests that are used to diagnose a disease or sickness are not always 100% accurate. Consider the following hypotheses for an individual who took a COVID-19 test. The null hypothesis is that the individual does not have COVID-19, and the alternative is that the individual does have COVID-19. So we have two possible types of errors that we could make. We could make the type 1 error, rejecting a true null, a false positive, or we could make the type 2 error, which is failing to reject a false null hypothesis or false negative. So all I want you to do here is decide what would a type 1 and type 2 error mean in this situation. So see if you can write a sentence down to describe what a type 1 error would mean and what a type 2 error would mean in the context of this problem. All right, we are almost finished with this section. To keep things organized, I've summarized everything you must do as part of a hypothesis test into 3 steps, which are detailed on the next few slides. Different instructors have a different number of steps that they might use. I've seen 5 steps, 7 steps, but I've boiled it down to just 3 steps. And we're going to be using these 3 steps for every single hypothesis test that we conduct. So the first step is to set up our null and alternative hypotheses. Now, some instructors might say that step 1 is to check your assumptions and make sure you've met all the assumptions or conditions that must be true in order to do your hypothesis test. And you probably should be doing that, but for the purposes of an intro class, I don't put that in one of my steps for my hypothesis testing. Obviously, in the real world, you want to check and make sure you've met the necessary conditions or assumptions, but more of my focus is going to be on just setting up the hypotheses and running the test. So my step 1 here is going to be setting up the null and alternative hypotheses. Your null hypothesis will always contain an equal to sign, as we saw before, and your alternative will always contain either a less than, greater than, or not equal to sign, depending on which type of test that you have. So if you have a left tail test, you should have some parameter, in this case I'm just using mu, is equal to, and then I'm just saying ... to represent some value that we would have that mean be equal to. Earlier we used 67, but it's going to depend on your specific problem. So no matter what, you should always have the equal to sign in your null hypothesis. And then your alternative hypothesis should have either a less than, greater than, or not equal to sign. If you have the left tail test, you're going to have the less than sign, indicating that you believe the true mean is less than some value. We could also have the right tail test, which has the same null hypothesis, but the alternative is now that the mean is greater than some value. Or we could have the two-tailed test, which now has the not equal to sign, indicating that you think the mean is either larger or smaller, but you're not sure which. Now, hypothesis tests can be conducted on other values, such as p or sigma, but I'm just using mu here as an example. So step 1 is to set up your null and alternative hypotheses. You will usually do this from some description based on a problem. And then step 2 is going to be to do your calculations, which involves finding something called a test statistic and then eventually calculating what is called a p-value. We'll talk more about those in the next video. First, you will calculate a test statistic, which is a number calculated based on a sample in a hypothesis test in terms of some corresponding distribution, such as the z distribution, t distribution, or later we'll use chi-square and the f distributions, which you may not be familiar with quite yet. If you're going to be doing the one sample mean test, then it turns out you would be using this formula. There's a different formula for every single different test, but there will be some kind of formula that you're going to plug in the numbers in from your sample to find, and this is what we call the test statistic. And from that test statistic, we're going to use some function, usually on the TI-84 calculator, to find the p-value. And so, for example, if you're using the one sample mean test, you would end up using a function called tCDF. But if you're using the z distribution, you'd use normal CDF or maybe some other type of CDF function. They're always going to be CDF functions from the TI-84 calculator. And we'll talk more about how that works a little bit later, but these functions can always be found on the second vars menu. So this is usually the largest or biggest step because it includes a lot of different calculations here. It's really two different things. First, finding the test statistic, and secondly, finding the p-value. But once you found those two things, you can make your decision and finally write a concluding statement. Now, the way that you make your decision is by comparing that p-value, which you calculated in the previous step, to the level of significance, the type 1 error rate. And it turns out that if your p-value is less than or equal to your level of significance, then you're going to reject your null hypothesis. And if the p-value is greater than the level of significance, you are going to fail to reject the null hypothesis. And, there's a saying that can kind of help you remember this. It is, if the p-value is high, then null will fly. Or if the p-value is low, the null has to go. So what that means is if the p-value is high, the null has to fly. That means that if the p-value is greater than your level of significance, you should fail to reject the null hypothesis. Or if the p-value is low, the null has to go. Means if the p-value is lower than your level of significance, you're going to reject your null hypothesis. Next, you're going to write a concluding statement that has this general template. You will state at the alpha percent level of significance, where alpha is whatever your level of significance was. Make sure to write that in percent form. There either is or is not enough evidence to suggest that, and then you are going to describe your alternative hypothesis. Make sure you are always describing your alternative hypothesis in terms of the conclusion, because that was like your research hypothesis that you were trying to test. And you want, when you finally write your conclusion, you want to state whether or not you did have enough evidence. You'd say there is enough evidence to suggest this, or not enough evidence to suggest the hypothesis that you put forward. So it's kind of like you as the researcher are writing, you're writing up your conclusion here, and you want to say whether or not your hypothesis that you put forward, if there was or was not enough evidence to suggest it. So for example, let's say that our null hypothesis was that the mean of some population was 20, and the alternative was that it was less than 20, what we call a left tail test. So here's an example of what it might look like to reject the null hypothesis with a 5% level of significance. you would say at the 5% level of significance, so make sure to put this in percent form instead of 0.05, we have 5% because that's the percent form of this number. There is enough evidence. We're saying is here, right? We had the option of is or is not, but since we were rejecting the null hypothesis, we're going to say is. There is enough evidence to suggest that, and then we would restate our alternative hypothesis in words, that the population mean is less than 20. Of course, you're going to write your conclusion in the context of your specific problem. So if your mean relates to, some kind of units, you would include those units in your conclusion as well. All right, so I think that completes everything I wanted to talk about here with regards to the introduction to hypothesis testing. In the next video, we're going to talk more of the details for the one sample mean hypothesis test. So I hope to see you in that video.